Hello everyone, welcome back. And today in this video we'll be talking about confidence interval for our regression coefficients. Regression coefficients, that is your beta 1 and beta 2. So in the last video we had talked about your confidence interval, okay, and when we were talking about your interval estimation. So your confidence interval is basically a range in which you are confident with some percentage, say 90% or 95%, that your true population parameter value might be lying. Okay, so that was about your confidence interval. So let's try to form a confidence interval for our regression coefficient also. Okay, so how do we do this? So we have learned about the Z statistic in our statistic videos. So we'll be using this because we know that the statistic follows your uh, standard normal distribution. Okay, so using that distribution we'll try to create a confidence interval, and we'll try to check whether our true population parameter is lying in that interval or not, and how confident are we about the parameter or the value of the parameter being present in that in that interval. Okay, so so we'll create an interval, we'll assign a level of significance, and based on that we'll check the probability of my population parameter being a part of that confidence interval or of that range that we have created. Okay, so or this can also be written as, this is beta 2 hat minus beta 2 summation xi square. So we have talked about this when we were talking about the variance and standard error of our estimators. So in that video we had discussed how these values are coming. Okay, so upon sigma, and this sigma is the standard error of the true population. So when we have the value of sigma we use z statistic, and if we don't have the value of the standard error for the entire population, we use the statistic. uh, so in this case we take the value of the estimated standard error. Okay, if we don't have the value of the entire population, we take the standard error of the estimator of sigma square, or sigma hat square, or uh, sigma square is basically your variance, sigma hat square is your variance of the estimator, and sigma hat is the standard error of the estimator. So we'll take that value. So your t estimator will look like, or t statistic will look like, minus beta 2 upon standard error of beta 2 hat. So this is basically your estimated standard error, or the standard error of the estimator. You can also, instead of using this, you can write this estimator of your uh, sigma. Okay, so you don't have the exact value of sigma, so you take the value of sigma hat, that is the estimator. So this is the right thing actually. It is the estimated standard error. So we don't have the exact standard error, so we take the estimated standard error. Estimated standard error. So I hope this is clear. So why we use, so we'll be using a statistic more rigorously, because we don't have the value of the standard deviation of the entire population. or the population parameter that we are trying to find out. So we take the sample statistic or the standard error of the sample statistic. Okay, so now we can create a confidence interval. Okay, so we can say that the probability that, so if alpha is my level of significance, so I'm going for a two-tailed test. Sorry. Okay, so probability that minus of t alpha by 2. So the value of t that I'm getting from here, okay, for alpha by 2 level of significance. So my level of significance we define beforehand. So if I say that my level of significance or alpha is 5%, so it means that I'm trying to create a confidence interval in which I can be sure by 1 minus alpha percent, or if the alpha is 5%, it means that I'll be sure by 95%. Okay, so since so these this is minus t alpha by 2 value, and this is t alpha by 2. So t distribution is also similar to, or kind of, or sort of, it resembles the normal distribution only. So this contains the 2.5% area, and this contains the 2.5% area, and the remaining 95% is here. So the probability that the t value, okay, that I'm getting from the t statistic lies in this range is equal to 1 minus alpha. Okay, so if alpha is say equal to 5%, it means that this becomes 95%. It means that out of 100 samples that I take, in 95% of the cases, my t value is present in this range itself, or it is part of this range itself. Okay, so I can say that I'm 95% sure that my true population parameter lies in this interval. So that is what is being represented using the t statistic. Okay, so we are creating a t statistic for uh, beta 2 hat. Okay, and we are trying to check from there that whether my population parameter value or beta 2 hat lies in this range, or how sure I am, like, of all the samples that I take, what percent of the samples contain the true beta 2 hat value in that interval range. Okay, so this is the case. So t alpha by 2 is the value of the t variable obtained from obtained from the t distribution. So you'll have to use the t table at a given level of significance and a given degree of freedom. Okay, t distribution for alpha by 2 level of significance and n minus 2 degrees of freedom. So this t distribution or t statistic follows your n minus 2 degrees of freedom. So basically there are two unknowns here. Okay, so that is why your degrees of freedom is restricted by two variables. That is why we have n minus 2. Okay, I hope you have the knowledge of degree of freedom. So we had discussed it briefly in the previous videos, right? So this is how you create a confidence interval using the t statistic, because you don't have the data to create a z statistic. So you use the t statistic and the t table and the t distribution. Okay, so this implies probability that t minus of t alpha by 2 beta 2 hat minus beta, I'm just putting the value of t here. Okay, standard error of beta 2 hat less than T alpha by 2 is equal to 1 minus alpha. So if I rearrange this whole thing, okay, if I take values here and there, so I get something like this: probability that beta 2 hat minus T alpha by 2 into standard error of beta 2 hat. Okay, beta 2 beta 2 hat plus T alpha by 2 standard error of beta 2 hat. So this is the confidence interval for beta 2 hat. So the beta 2, sorry, this is the confidence interval for beta 2 or the true population parameter, and it is lying in this range. Okay, and how sure about this thing we are, or how sure about this fact we are, that whether beta 2 is lying in this range or not, is being given by this value, 1 minus alpha. Okay, so if I choose a higher alpha, this probability declines. Okay, so if alpha is 10%, it means that I'm 90% sure. So if alpha is 5%, it means that I'm 95% sure. So this entire scenario is being affected by your level of alpha or level of significance that you are choosing. So this is something you choose on your own, or the statistician or the econometrician chooses beforehand, okay, while testing a theory or something. So we'll talk about this more in the hypothesis testing video. Okay, so we have created a confidence interval and we are this much sure, or the probability of my true population parameter, that is beta 2, lying in this range is this much, that is 1 minus alpha. Okay, so this means that this equation provides 100 into 1 minus alpha percent confidence interval, confidence interval for beta 2. Okay, and beta 2 is basically your beta 2 hat plus minus standard error of beta 2 hat. So this is coming from here in this, from this equation. So what this means is, this means that the width of the confidence interval is directly proportional to the standard error of the estimator, that is your sigma hat or standard error of beta 2 hat. Okay, right, so this implies larger the uncertainty, so larger the error or the standard deviation of estimating the true value of the unknown parameter, larger is the confidence interval, larger is the confidence interval. So if your confidence interval is very large, it means that your prediction is not that good. So if you say that my beta 2 hat or beta, sorry, if you say that beta 2 uh, value lie in the range of 10 to 15, so this is more of a precise estimate compared to if I say that it lies between 5 to 25. So as this range increases or this confidence interval becomes more wide, the reliability of my prediction or my estimation declines. Okay, so lower the uncertainty around estimating the true value of the unknown parameter, that is beta 2 in this case, better my confidence in estimating the uh, value of it. So I hope this is clear, and in the next video we'll talk about the confidence interval of sigma square. Okay, so till then take care and I'll see you in the next video.